Hello and welcome, everyone. We're really glad to have you here today for our weekly OCI Deep Dive. For anyone who might be new to these events, we're hosted on Cloud Customer Connect, which is our Oracle community forum for end users. And I'll be sharing some resources for you throughout the event today that will lead you back to those forums. If you're not already a member, we invite you to create a free account and you can join in discussions, post questions, look for upcoming events on all kinds of topics, and interact with other folks who are using Oracle products. My name is Kenna Kettrick. I'm a program manager with the OCI go-to-market team. And today I'm joined by Sujoy Chowdhury, principal product manager, and Sivanesh Selvanataraj, senior software engineer, to take us through the machine learning capabilities of OCI Data Flow. I think that's enough for me. So Sujoy, go ahead, take it away. It's all yours.
Thank you, Kenna. Hi, everyone. My name is Sujoy Chowdhury. I'm a product manager at OCI Data Flow. Today, we'll be talking about machine learning on streaming data with OCI Data Flow. We'll be covering a specific use case of manufacturing Lakehouse, doing predictive maintenance or predicting the remaining useful life of equipment. It will be also followed by a live demonstration. I'm joined by my teammate Sivanesh from the Data Flow team as well, who will be demoing some parts of it. So for some of you may already be familiar with Data Flow. Data Flow was a fully managed serverless Spark as a service in OCI Oracle Cloud Infrastructure. Customers can bring in their Spark applications, and they don't have to worry about, because we are serverless, they don't have to worry about the infrastructure. They can bring in their application, run their application, and we do the kind of management and kind of provisioning of the infrastructure for the customers. So we have introduced the streaming feature recently in Data Flow, so that previously you could only do applications that kind of were batch in nature. You kind of ran the application and it after processed a finite amount of data and it completed. Now you can process infinite data that is infinite in nature, essentially, that is continuously coming in. You can continuously process, and you can use the kind of the streaming capabilities of Spark as well. So some of you may not be familiar with Data Flow itself. So let me start with a quick demo and then kind of do my rest of my presentation. So today we'll be talking about the manufacturing lakehouse that constitutes of 3 applications. But if you're not familiar with this, let me quickly show you how our application is created. If you come to OCI Data Flow console, you create an application. You define the application by providing the URL of the application and the data that you want to bring in. You define the resource. For example, here you're defining the driver shape, the executor shape, and then you kind of create the application and you run the application multiple times. That's how we do. So we already have 3 applications. One of them I'll be actually starting now, so that by the time we get there, the run will be completed. This is a trainer application. It will train a machine learning model that we will be using for predicting remaining useful life for an equipment in a streaming application. So let me run this. You'll see that it has the name, it has a driver shape configuration already here. You can provide arguments, and as I click on run, Data Flow service accepted this submission. It will then provision the resources behind the scene. It will take about 3 to 4 minutes to process about 600 megabytes of training data. And it will it will read the data from the object storage. It will write it back to the model back to the object storage. But before that, let me come back to the demo part of it later in the presentation and cover some of the other things we wanted to talk about today. So so we talked about data flow. You just looked at data flow, but and some of you may or may not be familiar with the Lakehouse concept that we have. And data flow is a part of this Lakehouse. You can see that Data Lakehouse is a flexible open architecture that lets you bring in any database, any application, any cloud, any events to your platform. And we have the managed open source services. One of them is Data Flow that lets you process using all the data using the power of Spark. So we are, of course, we have many other services in Lakehouse that kind of are deeply integrated with each other so that you can really innovate using all your data at the same time. And today we'll be focusing mostly on streaming data, how you can use data flow to process your stream data and to kind of do machine learning, to do all kinds of prediction, specifically on the manufacturing use case. So a little more on the Lakehouse. So in a Lakehouse, we combine the architecture of data lake and a data warehouse so that you can get the best of both worlds. As you know, you may prefer to have your raw data or unstructured or semi-structured data in the data lake, processing the data lake before you want to put it in the data warehouse. You may data warehouse is, of course, is best for your structured data for all kinds of performance reporting. So you have that option to, if you want to optimize before putting data in your database or data warehouse, you can do all the cloud scale ETL and machine learning before you put things in data warehouse. So in this case, we'll be doing cloud scale ETL at OCI Data Flow. And one of the capabilities of Data Flow being a managed Spark service is it can do stream processing. It can do machine learning on top of stream data. And also, you are not limited to any specific language. You can bring in if you have that data scientists in your team who want to do Python notebooks, for example, or if you want to do Java-based application, you can bring those in. You are not limited to SQL, for example. Great. So we can do we can use all our data to innovate in a Lakehouse, and Data Flow will help you to do cloud scale ETL and machine learning on all your data that you bring into the Lakehouse. Now, if we zoom into the Data Flow specific piece of the architecture we just showed, you'll see that it can take in from OCI, it can use OCI streaming and object storage or data lake as sources. And this OCI streaming as a source was not supported until recently. So that's that's great, so that you can now process stream data. Not only that, it can take stream data as a source, it can also write back to a stream, write back the processed data into a stream. It can, any Kafka compatible stream or message queue as it can be used. It can write back to object storage or even ADW or any other downstream services or sinks. It can continuously retrieve input data. You are not limited to just hourly or daily jobs. It can continuously make that data available. You don't have to wait until the application completes. If there is an outage, you don't need to do job restart because it can continue from the last checkpoint that has been defined. The beauty of streaming application on Spark, on a Spark infrastructure like Dataflow, is that it can handle late data and watermarking so that you can catch up if you have any backlog data over time. It can do, you can use the best in class processing, the heavyweight processing that Spark enables you in a distributed platform. It can do the heavyweight stream joins, and most importantly, it can do machine learning. It has the built-in library called MLLib, the Spark MLLib that can be used to do about a lot of machine learning use cases, one of which we'll be focusing on today. So we'll be touching on, you can do a lot of different, you can build a lot of different lake houses focusing on different industries. For example, for manufacturing, you can predict remaining useful life of your equipment before or predict when it can before the failure actually happens. So in a financial services lakehouse, you can predict the fraud before kind of if you see suspicious transactions coming in from the stream data, you can use that to predict that kind of fraud. In a telco, if you analyze your CDR as a stream data, you can use data flow streaming to process to build a lakehouse that can predict customers who are at risk of churn. So we'll be focusing on the RUL use case today. So that will help you to predict remaining useful life, the amount of time you have left for your equipments using data flow and Spark. Okay, so kind of a little bit more about what we'll be showing today. You have seen the 3 applications earlier. We have the trainer app, the simulator app, and the predictor app. The most important app, the predictor app, is the streaming app that does the prediction. It is informed by the model that is that was done, kind of trained by the trainer app, and it takes in the simulated sensor data coming in from a factory floor, using which it can predict the remaining useful life of an equipment. And just for our demo today, we'll be using kind of the red, yellow, green terminology. So if the remaining useful life of an equipment is between 10 to 30 days, it would be considered as red, so that it require immediate performance, immediate maintenance. If it is between 30 to 60 days, it will be yellow, so it should be kept under watch. And if it is more, remaining useful life is more than 60 days, is healthy, and no action will be needed. And this predictive maintenance or predicting remaining useful life use case is very important in the context of Industry 4.0 or the fourth industrial evolution, they say, because you really don't want to wait until your equipment fails. For example, think about an airplane engine. You don't want to wait until it fails. You want to predict the failure before, well ahead of time, and replace the parts or do the maintenance. So out of the 3 different kinds of maintenance you could do in a manufacturing or industrial scenario, the best in kind is the predictive maintenance. It can predict the trend and estimation when maintenance is required. The worst in kind would be the reactive. So you do the maintenance after things fail. And you could also, typically what we see is preventative maintenance, which is planned and scheduled maintenance. Sometimes you do the maintenance even if that is not needed. You replace parts just as a precaution, even if that's not needed. That could be wasteful. So that's why we kind of this predictive maintenance use case is very useful in the manufacturing scenario. And in order to do the predictive maintenance, we'll be using kind of the survival analysis, which is a kind of a branch of statistics that analyzes expected duration of time until one event, specific event occurs. That event is the mortality or death or malfunction of that equipment in this case. We'll be using the power of Spark to analyze, to do machine learning, to do a survival regression model, to conduct that survival analysis. And we'll be doing a specific, you will be using a specific technique called accelerated failure model, which is, again, it's a accelerated failure time model, or AFT model. That's a parametric model that kind of comes as one of the canned options in Spark MLLib. It's also kind of an alternative to the commonly used the proportional hazard models. So the proportional hazards model assumes that the effect of kind of covariate is to multiply the hazard by some constant. An AFT model assumes that the effect of a covariate is to accelerate or decelerate the life course of a disease by some constant. So this is especially appealing in a technical context where the disease is a result of some mechanical process with a known sequence of intermediary changes. And this AFT model is also useful to parallelize, which is kind of because each instance in your Spark cluster contributes to the objective function independently. I'll not get into the math part of it. You can look that up. This is publicly available in the Spark documentation. So today we'll be actually doing a little bit of our rocket science because our training data set literally comes from NASA, is the turbofan engine degradation simulation data set that comes from the NASA Ames prognostic data repository. This degradation, this degradation data set actually was done by run to failure simulation using a tool called CMAPS. So the turbofan is a kind of combination of turbine and a fan, and it's a mechanical. It has a lot of moving parts, as you can see listed kind of in the diagram below. It has so there is lots of opportunities of failure, and it has plenty of sensor data coming in the top right. You can see about 21 sensor data measuring the temperature, measuring the pressure, measuring the fan speed, and so on. So we'll be using this training data set to create a machine learning model on RUL first, and then use that model. That training would be I mean, the app that I started that is doing that processing right now, that model is will be saved in object storage, and then the streaming application will be using that model to predict remaining useful life for the real data that is coming in as stream. And so this is kind of, you will have in the data set, there is you will have the, for example, the engine unit number, the time in days remain kind of, or time cycles remaining, how many operational settings are there, and of course all the 21 sensor data that comes from the data set. We will be using, so I showed you the 3 sample apps that we have, one of which did the training, and we'll dive a little bit into the code part of it to see how that works really. So you see the training, the model trainer has 3 or 4 steps. The first part is training, of course, preparing the training data. You can use the vector assembler that comes from Spark ML library to process the data, pre-process the data, clean the data. For example, in line 35, 36, 37, this vector assembler is a transformer that combines a given list of columns into a single vector column. It is useful for combining raw features and kind of feature generated by different feature into a single feature vector. So in order to train machine learning models like logistic regression and decision trees. In line 38, you're looking at kind of normalization or scaling of the sensor data. Think of, so all the different sensors, the 21 sensors that are coming in, they are having different ranges of numbers, right? A temperature range would be different from a pressure range. So what the model is doing is it's normalizing it from between 0 to 1 so that you can use that normalized number, the scale number, for training. So that is happening in line 38. So after that pre-processing and scaling and the normalizing is done, then you will train the model using that AFT survival regression technique that we just talked about. And finally, after the evil model is trained, you provide the parameters, what are the scale features, how many iterations you want to run. And then you kind of save the model. After you evaluate the model, you save the model, write it back to the object storage. As you can see in Scala, specifically, it's this training requires less than 60 lines of code. Tiny app that kind of does that offline training for you. Now, this is what kind of the app or that would look like after the run completes. You'll see that shortly when Sivanesh shows you the remaining parts of the demo. So this is, we provided all the, that app, all the kind of horsepower it needed to run. And it takes about 3 minutes to run. It processes about 670 megabytes of data and out generates that 6 kilobytes of the model that is size 6 kilobytes. So you have all the different metrics and logs that are for that run. Those are actually stitched together for you by the Data Flow platform, because we manage the cluster, we manage all the relevant pieces for you there. And you'll see that shortly in a little more detail as Vanesh demos later. So the second app is we showed earlier was a simulator app. We are using a simulator because we really don't have a turbojet engine at our disposal right now. So, and Spark actually allows you to simulate sensor data by a source called rate source. So you can see in line 113, you can use the read stream kind of, or you can create a stream that's like a rate source. But before we get into that, I talked about the 21 different sensors. This is kind of how the sensor data kind of look like. It kind of have to configure the different ranges. This kind of sensor, this simulation or simulator app will be simulating this 21 different sensors using the ranges that we found from the training data set earlier, right? So that the simulation is kind of realistic. And we'll be doing the prediction on top of that simulated stream. Now, when we are simulating the data, we want to ensure that it has all different kinds of data. It has both the red, yellow, and green. So we'll be kind of putting in mostly green numbers. So we'll have about 100 records per 10 seconds in the stream that is green, about 3 records that are yellow, and about 2 records that are red. And we'll be using that simulate, and that will be done randomly as you can see in the code. So in the code, after you have the simulated stream, you can do the prediction and apply your machine learning algorithm there. So the next app after the simulated simulation is done is the actual app we wanted to talk about in detail today and demo in detail today is the predictor app. The predictor app reads the stream from the OCI stream source. It takes in the model that was the from the object store. It reads the model from the object store that was generated by the trainer app earlier in Data Flow, and then it does the prediction. It does the RUL prediction. If it is green, it writes back to a stream. If it is red or yellow, it writes back to data warehouse so that you can do further processing. And a little peek into the code. If you see at the beginning line 26 to 35, you can configure how you are the different Kafka compatible parameters to read the Kafka stream that is generated by the simulator app. Then you, in step 2, there are 7 steps. I'm just giving a high-level overview of what those steps are looking like. So you encode the stream and encode the data to the schema. In step 3, you load the model that you generated earlier from object store. And step 4 is predicting RUL, of course, using the AFT model. So when you kind of predict RUL, you kind of will have, you kind of want to still do some of the denoising aspects. So we talked about the vector assembler in the Spark MLLib that allows you to do that. You still do the scaling on the data that is coming in, and then you are kind of categorizing the sensor stream data into one of the three categories. Either it is green or yellow or red, right? And if it is red or yellow in kind of step 7, you write it to data warehouse, because these are most important data you want to look at, you want to take actions on. If it is green, you can, in step 6, you write it back to another stream. And you may want to do online kind of machine learning training on top of that green data, or you can use that data stream to really ensure that it is running okay. There is no faulty behavior, faulty kind of prediction there. So those you can kind of you have that stream to do that further analysis later. So this is time to kind of go back to the app and see a little more in more detail how the different streaming app is doing, specifically the predictor app. And I would like to hand it back to Sivanesh to show us the predictor app in detail in OCI Data Flow console. Sivanesh, take it away.
Thank you, Sujoy. So I'll just share my screen. Okay. So quick recap of what Sujoy was talking about. So there are 3 apps. So we have a trainer, which is an offline batch application. And the second one is the sensor data simulator, which simulates the sensor data and write it to a stream. And third is the real-time RUL predictor, which predicts the remaining useful life in real time and writing to ADW as well as writing to another stream. So I'll just switch back to my console. Okay, so to start with, so this was the app that Sujoy started at start of the presentation. So this has completed. So as Sujoy was saying, it took 3 minutes, 39 seconds to complete and took in 651 MB of data and produced 6 KB of model, the trained model into object storage. So I'll just go back. So this is the object storage location where the model is stored and all other things. So this is the actual application that was packaged as a jar and that we are using. And this is the test and training data that that Sujoy was talking about, the NASA turbofan test data. And this is where the models are stored. So this is the survival model, so which is actually going to predict the remaining useful life. And this is the scalar model. So this will be reused, what we used in the training in the streaming application to scale the sensor data to a single unit. And this is the features model. This has a vector assembler model that collects the features from the incoming data and create a training, like a data that can be used for prediction. So we will be loading these models into our streaming application and reuse it. Okay, so I will, so this one, the checkpoint. So this is the metadata checkpoint for the streaming application. So this will preserve the state for the 2 streaming applications that we are going to see, the simulator and the predictor. So the simulator, so that we can, so if you want to stop the start the streaming application from where it stopped, so this is required for the Spark structured streaming applications. Okay, and I'll just quickly show the little bit data. So this is the schema of the training data. So this is the output of the or the logs of the application that Sujoy ran. So this is the schema of the sensor data that that is incoming data, and this is just a sample data, and this is some stats on the data, how many max min standard deviations, and we label the data. So this is the extra labels that we added to the data, and this is the output of the label data, and we persisted the data as I was showing in the object storage. Okay. Okay, so these are the two streaming applications that we are going to see now. So the sensor data simulator is going to randomly simulate some data, sensor data, and write it to OCI streaming service. So this app is running. So I will just go to OCI streaming and quickly check if the data is coming. So this is OCI streaming service. And this is the input stream or the output stream of the sensor data simulator. So where the data is getting generated. So our sensor data simulator app is generating the data here. As you can see here, the data is coming in right now. So it generates every 10 seconds a mixture of like a different RUL records. So this has the same schema. So the equipment ID and sensor data and the event time. So we are going to use this sensor, this stream. We are going to consume this stream in our real-time prediction app to consume and predict the remaining useful life in real time in the third app. So I'll just go back here. Okay. So so this is our application, the real-time predictor application. So this one takes the input input from the stream that we have just seen. So we have just saw. So so this will take the input from this stream and run every two minutes and predict the remaining useful life. So this app is up and running. So I'll just go to the Spark UI of it. So this is the Spark UI for that the streaming application, the remaining useful life application. So this is live Spark UI as it is running. So there are like different tabs. So this is you can see all these the first 6 tabs in Spark batch application as well. Though this provides some information about like, so the jobs will provide some information about like what are all the different jobs and how long it takes. And so if you are familiar with Spark, so the Spark runs with like a job, stages, and tasks. So this the stages will provide the insights about the stages. And the storage will, if you persist any RDD or a data frame, and it will show the information about those RDDs here. And the environment just shows the Spark environment variables like Spark configurations, Hadoop configurations, all those things. And the executors will show the executor, the list of executors live, date. And this one shows the batch SQL queries. And this one that we are interested in, so this is the structured streaming. So this will store the stats about the streaming queries. So this one, the input rate. So this tells like the what is the input rate from the stream that we just saw, like what is the input rate that we are receiving the data, and how fast our application is processing. The streaming application is processing the data. And this one so structured streaming application run in micro batches. So so there is a trigger. So every 2 minutes, as we seen in the UI. So every 2 minutes, this application, the micro batch will trigger and run. So this is the number of input records that was processed in each micro batch. And this is the batch duration, the micro batch duration. And this is a breakup of the batch duration. So this has the add batch. So this is the bulk of the time. So the add batch indicates like how long you take to get the data from the stream, process and write it to the sink. And the get batch is how long it takes to get the data from the stream, the incoming stream, and the latest offset, like so how long it takes to get the latest offset from the stream. And this is the how long it took for the execution, create the execution plan for the process. And how long it take to, this one is wall commit, is how long it take to commit the checkpoint into object storage. So this is the brief about the Spark UI. Okay, so as the application is running, the real-time predictor is running. So it is writing to two output sources. One is autonomous database for the yellow and red records, where the RUL, the remaining useful life, is less than 60 or less than 30 days. And the second one is the green records. We are writing to the another stream. So I'll just show them. So this is the input stream that we have seen before. I'll just step back. So this is the output stream where we have the predicted RUL. So since the RUL prediction app is running, so the data for this is also coming, should be coming. So this is all the green records, which has the predicted RUL and the category of the record that we categorize based on the threshold. So this data can be reused again for like a online training. So we can train our model continuously and reuse it. So we can reuse this data and make our the batch training application to streaming as well, to make it really like a continuous learning of the model. So we can feed this data to the model. And the second output is the autonomous database. So we have an autonomous database already up. So so this is the data coming in. So I'll just quickly refresh. So as the data is coming in, so it will write the red and yellow remaining useful life records here. So anything less than 30, which is we categorized as red, and anything greater than 30 RUL we categorized as yellow. So we write to autonomous database in real time as it is as we are processing. So we can further build application on autonomous database, or we can send alerts, or we can actually create a manufacturing maintenance work orders from here. And this is just a quick insight of the data that is coming in the autonomous database. Yeah, so that's all from me. Back to you, Sujoy.
Thank you, Sivanesh. Let me share my screen again. And so we just saw the demo on predicting remaining useful life from the simulated stream data in a manufacturing lakehouse. We showed how the three apps in Data Flow are contributing to support to kind of do that prediction. We had the survival model trainer that initially trained a model based on a data set from turbojet engine jet failure. It created an offline model. It read the data from object storage. It created an output model into the object storage as the first app. The second app, the sensor data simulator, it looked at the ranges in the training data set, and it simulated a stream so that we could do the prediction in real time. So it created a simulated stream that the real-time predictor app used as a source to predict RUL, the red, yellow, green remaining useful life prediction that we really need to do the maintenance on the equipment. Now, a few pieces I wanted to kind of touch on here. you have seen how the Spark UI that is managed by OCI Data Flow that kind of shows you in real time how your Spark infrastructure is doing. You can look at the query. You can actually dive deeper into the streaming related the input rate, process rate, the batch duration, how the different jobs are performing. You can think of if you want to give more horsepower to your streaming app or not. You can also do auto scaling. This is Spark streaming that the Spark UI that is already fully managed for you inside Data Flow. You do not have to really worry about how to, for example, if your cluster is running out of disk space or it needs maintenance, you can just focus on your application. You can just focus on whether it's working properly or not. You can look at the you can think about at the application level rather than at the infrastructure level. So that is where the beauty of Data Flow is. You can also think of you have also seen how Data Flow wrote to the ADW using a single line of code here. We use a data source called Spark Oracle Data Source that enables you to do that. This is not actually coming from Spark. This is our contribution to the Spark, so that it may you have a streamlined approach to read and write to any Oracle data source. And you have seen the output of that kind of write to ADW here when Sivanesh was showing you the red and yellow RULs in the ADW. Finally, Sivanesh also showed you the logging integration, where within the Data Flow app, you have the link to the real-time streamed logs coming out directly from your Spark cluster, so that you can, for example, this is faster, better, filterable, searchable log offered by the OCI Logging service that you can kind of use further. And it is all deeply integrated for you within the OCI Data Flow service, so that you have the fully managed experience of Spark. So Data Flow continues to be the fully managed Spark experience with all these deep integrations, with all this kind of cloud native authentication, the end-to-end exactly once fault tolerance. We add all the we add additional fault tolerance on top of Spark, so that, for example, if your run stops due to some infrastructure glitch, you don't have to worry about it. We will resubmit it for you. If we need to do the monthly maintenance, for example, or some other glitch happens, there will be graceful shutdown of your app, and we will then kind of resubmit the job so that it can start. So this automatic fault tolerance, automatic patching, the fully managed experience, these are all things that you're getting from Data Flow, being the fully managed serverless Spark service. And of course, we are not really adding any markup on top of the infrastructure cost here. So that makes Data Flow the one of the most cost-effective ways, if not the most cost-effective way, to run Spark application on OCI or any cloud. So thank you for listening to us. We will actually answer some of the questions that we have had throughout the session. We had a few questions on Data Flow and Data Flow and Golden Gate that I would like to touch first. So you have seen that Data Flow, this is a managed Spark service, serverless Spark as a service. Golden Gate is another service that uses Spark, and it can also do stream analytics using the same Spark engine that Data Flow provides. And Golden Gate has a few built-in patterns in the GUI that is exposed itself. One key difference is in Golden Gate, you will have to do a lot of DIY on the cluster, the Spark cluster. On Data Flow, things are fully managed for you. And we kind of have shown examples like how you don't have to think about the cluster. The cluster is provisioned after you submit the job. For example, different OCI services are deeply integrated in that experience that you can only get in OCI Data Flow. So that's the Spark engine. There were questions on predicting revenue models using data flow on OCI. Of course, you can do that. So this was a manufacturing demo or manufacturing industry Lakehouse demo, where the stream data source constituted of sensor data coming in factory floors. If you replace the sensor stream by a stream that is a kind of transaction data coming in from the point of sales from different parts of the world, say you kind of want to look at all those transactions from different POS terminals, and you want to predict the revenue and at the end of the month, you can actually use data flow to do that in real time, using not just the data that came in the last 5 minutes or 10 minutes or 1 day. You can use the full data. That is the beauty of Spark being the distributed big data platform. You can use the full data that is in the stream, the source stream, to predict the revenue model, say production, estimated forecasted production, or anything of that like. There was a question on whether data flow can be used. I believe there was another webinar earlier where we showed using some wearable sensor data to predict. It's a healthcare related use case. You can also build healthcare related lakehouse, similar lakehouse, and you can do likely similar processing on data flow. You can, for example, you can think of data streams coming in from your glucose sensors, and you can predict the risk of an acute diabetic situation where you need immediate intervention. So that can be done using data flow. You can, for example, if you have a Fitbit or any other wearable, you can look at your blood or your heartbeat data. You can predict whether your patient is at risk of arrhythmia or some other heart condition. That can be done using the power of structured streaming or Spark streaming on data flow. Using the same or similar techniques of you can take it in any stream or any data in object store, analyze using Spark, MLLib, and do the outputs as prediction into the streams or autonomous databases or data lake, whatever sync you'd like. So Spark is the generalized distributed Spark processing platform, and we are offering you the fully managed version of it so that you can use the full kind of power of Spark with the deep OCI integration, the cloud integration, the cloud native security model, and so on. Okay. I want to talk about a little more about this kind of cloud native security as well. So if you remember at the beginning, we had the batch application or data engineering application where we trained the model. It finished automatically. You did not have to think about the cluster had to be terminated. I mean, the cluster was deprovisioned on behalf of you. And so that's one pattern where you want to process application that completes and that runs periodically. But then the streaming application is different in nature, right? So it requires a different type of cloud native authentication. So we have the resource principal support so that your apps can now run beyond 24 hours. So if you have a kind of batch application that you can use your previous ways of cloud authentication, and you can now use for streaming apps, you can use the resource principal based authentication, which is offered by OCI Data Flow. Okay, you see if there any other question. Yeah, so there's a question on revenue model prediction. Looks like we have a lot of interest in the financial services industry. We will have, so you are looking at the GitHub link below. So we will be publishing first the manufacturing Lakehouse source code and live labs there. We will also have financial services industry use case, and looks like there is some interest in the revenue model prediction area. We can kind of pick up that use case and have a high level slide and kind of demo there as well. Any other questions? I really encourage you to really go to the GitHub. Try, if you're not familiar with data flow, you can try out the different sample apps. Actually, if within the console experience of data flow, you have the option to create a sample app. It will create an app for you, and you can run and you can understand how data flow is kind of offering the fully managed experience for you. Streaming apps are, of course, a little more involved. It requires, you have to set up the stream data. You have to set up you have to have either the simulator or the actual data coming in. So, but we have today tried to show you how within less than 150 lines of code, you can do a prediction on any industry. You can do a kind of RUL prediction in, for example, Lakehouse, manufacturing Lakehouse example. You can do similar things on financial model. We'll probably publish some code later on that. You can do similar prediction in the healthcare industry or in the telco industry. The underlying engine remains the same. The pattern remains the Lakehouse pattern remains the same. The code would be similar. The data will have some nuances. The processing detail will have nuances. You'll probably be using a different model. It will not be a survival kind of regression model for example, for revenue model prediction. It will be a different model. And you can bring in your own algorithms. You can use the built-in algorithms that are coming with the Spark MLLib. So you can do you can support all kinds of general purpose machine learning use cases for any industry for this distributed Spark platform.
All right, we can give it a moment if there's any other questions that people are wanting to drop in there, but I see Sujoy has also shared contact information, so you're open to being reached out to a little bit later if folks are playing with the code or curious about things as well. I'm going to launch one final conclusion poll. If folks wouldn't mind giving us some feedback on that, we'd appreciate it. And I just want to say a really big thank you to Sujoy and Sivanesh for joining us and for sharing all this information. I've shared the link where the replay and resources will be, so you should be able to go and take another look at this and check it out later, dive a little deeper into some of these topics. And we really appreciate all of your time, both the audience for joining us and the presenters for sharing their time and information with us. So thank you so much, everybody.